Welcome friends. In the last class, we have discussed the inductance of stranded conductor, and we have seen the inductance formula is given by the two new terms. One is geometric mean distance and another one is geometric mean radius. And we have told that this GMD GMR method is quite useful to calculate inductance or capacitance of any transmission line configuration or tower configuration maybe without deriving any complex mathematical derivation. So in this lecture we shall see two problems of different configuration, of course, and we shall see how the inductance can be calculated quite easily by using this GMD GMR method. Let's proceed to our problems. Suppose we have this problem. You see that this is three-phase double circuit line. This is an example of three-phase double circuit line, and of course with a symmetrical spacing. We have a symmetrical spacing configuration, and these 6 conductors are placed at the vertex of hexagon. Okay, regular hexagon, or not regular, rather the lengths are not same. The 6 conductors are placed at the vertex of hexagon. Now you have a formula L is equal to 2 into 10 to the power minus 7 ln dm by ds. Now, in order to calculate this dm, you should know the following. What is dm? It is the mutual distance between two phases. So you have to first identify, or you have to first calculate what is the mutual distance between A and B. Second, you need to calculate what is the mutual distance between B and C. And third, you need to calculate what is the mutual distance between A and C. Once you have done, you need to come to this term ds. So what is self distance? When you calculate, then you need to first compute what is the self distance of phase A. Then you need to calculate what is the self distance of phase B. And lastly, you need to calculate what is the self distance of phase C. Now we need to figure out, when you calculate the mutual distance between A and B, what are the different possible combinations, or what are the different possible distances existed between A and B phase. Let me figure out. In between A and B phase, we have first distance A1 and B1. We have first distance A1 and B1. So this is the distance. So how should you calculate? Suppose this is a right angle triangle. Now this is 3.5 meter. This is 3.5 meter and this is 1 meter. Why this is 1 meter? Because this total is 8 and this is 6. So this side, left to the A1 it is 1 and right to the C2 it is 1. So A1 B1 is nothing but 3.5 whole square plus 1 square, which is equal to 3.64 meter. 3.64 meter. Then coming to what is the next distance possible, A1 B1, it's gone. So next possible distance is, you see, it is A1 B2. A1 B2. A1 B2. What is A1 B2? So this distance is A1 B2. So how you calculate? Again you need to consider this right angle triangle. So this is 7 and this is 3.5. So A1 B2 is nothing but 3.5 whole square plus 7 square, that is found to be 7.83 meter. possible combinations to be A2B1. A2B1. What is A2B1? A2B1 is this distance. Now luckily, due to the symmetric nature, A1, B2 and A2B are exactly same. So A2B1 will be 7.83 meter. And finally, we have A2B2. A2B2, this distance. Again, by the symmetric nature, this A2B2 and this A1B1 are exactly same. So A2B2 is nothing but 3.64. So when you calculate the mutual distance between AB, you should consider all these four distances. So you should take the fourth root. So we have 3.64 twice. So we have 3.64 twice. So you should take square, and then you have 7.83 twice. 7.83 twice. So you should take the square. So in other words, you can write this expression as 3.64 into 7.83. That is equal to, that is found to be, that is the mutual distance between A and B is 5.34 meter. 5.34 meter. So we have calculated the mutual distance between A and B as 5.34 meter. So in this way, all the dm or ds should be calculated. Now let us coming to what will be. So we have calculated DMAB. Let me write it down. We have calculated DMAB as 5.34 meter. Now let us consider in between B and C. Let us consider between B and C. So we have similar sort of combinations. We have similar sort of combination. So first we have B1 C1. First we have B1 C1. This distance. Again, this distance is nothing but 3.64, because this is 1 meter and this is 3.5 meter. Second, we have B1 C2. Second, we have B1 C2. So same thing. B1 C2 is this distance. So this is the right angle triangle. So this will be 7 meter and this will be 3.5 meter. So again, this is 7.83. Third, we have B1, so B2 C1. B2 C1. So B2 C1 is this distance. So this will be same as that of B2 C1 because of the symmetry. And finally, we have B2 C2. Finally, we have B2 C2. It is this distance. It is exactly same as that of B1 C1 due to the symmetry. So we have B1 C1 3.64, B1 C2 7.83, B2 C1 7.83 meter and B2 C2 3.64. So similarly, DMBC can be found out exactly by the same formula. DMBC can be found out by exactly by the same formula. So we have evaluated DMBC as 5.34. Lastly, we have DMAC. 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 Now, what are the possible distances? First, we have First we have A1C1. First we have A1C1, which is equal to 6 meter. Second we have A1C2. Second we have A1C2, which is equal to 7 meter. Third we have A2C1. Third we have A2C1, which is equal to 6 meter. Third we have A2C1, which is equal to 6 meter. So I am writing here A2C1. So we have A2C1, we have A1C1, we have A1C2, and finally we will have A2C2. We will have Sorry, I have done one mistake. It is, I think I have done one mistake. First A1C1, which was equal to 7 meter. And second we have A1C2, we have it is 6 meter. Okay, now it is fine. Third we have A2C1, this distance, it is 6 meter. So it is A2C1. And fourth one should be A2C2, which is equal to 7 meters. So in this way, we can calculate DMAC, which is nothing but, there are 4 terms. So we have 6 squared into 7 square. It should be into. So it will be square root of 42, which is equal to square root of 42, which is equal to 6.48 meter. So we have calculated DMAC as 6.48 meter. So once you have calculated all the 3, then you should calculate what is the mutual distance equivalent. So it should come DMAB into DMBC into DMAC. Now you have 3 terms, so you should take cube root. So what is DMAB? That is the mutual distance between A and B. It is, I think, it is 5.34. Yeah, it is 5.34. DMBC is also 5.34, so it will be square. And lastly, we have DMAC equal to 6.48. 6.48. So if you take the cube root out of this, you will get the result. DM is equal to 5.7 meter. So we have evaluated the length of this tower configuration as 5.7 meter. We will require this data at the last. Now you should evaluate self distance. To evaluate DS, again the same thing. What is DSA? In order to evaluate DSA, you should find out the 3 or let us investigate what are the possible distances possible. Now first of all, the first distance is A1 to A1. Okay, first distance is A1 to A1. First distance is A1 to A1. What is that? A1 to A1, basically it is the radius of that conductor. So A1 to A1 is basically the radius of that conductor. Second, we have A1 to A2. Second, we have A1 to A2. What is A1 to A2? What is A1 to A2? A1 to A2 is basically this distance. So it is this is 7 meter, this is 6 meter. So A1, A2 basically it is square root of 6 square plus 7 square. That will be equal to, it is I think 9.22. 9.22 meter. Then we will move next, then A2 to A1, which is exactly same as that of 9.22 meter, and finally we have again A2 to A2, which is again it is equal to R. So once you calculate DSA, that will be equal to DSA, that will be equal to, it is basically, it is the radius, but you know in case of inductance calculation it should be multiplied by 0.7788. What is the radius? Radius is conductor diameter is 2 centimeter, so radius will be 1 centimeter. So it will be 0.01 into 9.22, so that is found to be 0.1436. 0.1436. You can verify these values at your own. Okay. Now what is DSB? What is DSB? So DSB is nothing but the self distance of B phase. Self distance of B phase. So basically, what is DSB? DSB is the self distance of B phase. So it is actually, let me explore what are the possible distances. First is B1 to B2. First is B1 to B1. First is B1 to B1, which is equal to R. And second one is B1 to B2, which is B1 to B2, which is equal to 8. So what it will be DSB? It will be square root of 0.7788 into 0.01 into 8, and that will be coming out to be 0.1246. And finally, when you have calculated C, it will be coming as same as that of DSA, which is 0.1436 meter. Why? Because when you calculate C, it is exactly same as that of A because of geometry. So C is C1, which is R, and second one is C1, C2, which is the exactly same as that of A1, A2. So once you have calculated all these three, so equivalent DS, that is the self distance equivalent, which is equal to product of all these three, and then you should take cube root. So we have 0.1436 twice, so you should take square, and then 0.1246. It should come out to be a 0.137 meter. So you have calculated DM, we have calculated DS. Now we will calculate the final value of the inductance, which is 2 into 10 to the power minus 7 ln dm by ds. So which is equal to 2 into 10 to the power minus 7 ln, what is dm? Dm is 5.7 meter, DM is 5.7 meter and DS is 0.137 meter. So if you evaluate this, it will be coming out to be 7.456 into 10 to the power minus 7 Henry per meter, or it can be written as 0.07456 millihenry per kilometer. So if you have a tower configuration like this, right? If you have a tower configuration like this, and if you run this tower for 1 kilometer, it will provide an inductance value of 0.07456 millihenry. 0.07456 millihenry per 1 kilometer of run. So as you can see, this is a three-phase double circuit line. We have evaluated inductance value, but we don't require any complex derivation. So this is the advantage of this GMD GMR method. Let us solve another problem. This is this is a single circuit scheme. This is a single circuit scheme with bundle conductor. This is a single circuit scheme with bundle conductor. Now you see this A1 A2 constitutes a bundle conductor. This represents phase A. B1 B2 constitutes a bundle conductor that represents phase B, and this C1 C2 constitutes phase C. It represents a bundle conductor with phase C. So we have A phase, B phase, C phase. So it is a single circuit. Conductor diameter is 1.2 centimeter. So let me evaluate one by one the same process. We first evaluate DM, then we shall go towards DS. Now what is DM? We first evaluate DM. So we have DM AB, that is mutual distance between AB. So let us explore how many possible distance. So first distance could be A1 to B1. A1 to B1. Second distance could be A1 to B2. Third distance could be A2 to B1, and fourth distance could be A2 to B2. So you have 4 terms, so you should take fourth root. So what is A1 B1? So A1 to B1 it is 10. What is A1 to B2? It is A1 to B2 is 10 plus 0.4. So it will be 10.4. What is A2 B1? What is A2 to B1? This distance is becoming 10 minus 0.4. Because this is 40 centimeter, right? This is 40 centimeter. So it is 9.6. And lastly, A2 to B1, it will be 10. So once you have calculated, you will get this result as 9.995 meter. 9.995 meter. Now once we calculate similarly DM mutual distance for BC, you will get the same result. Between B to C phase. It will represent the same result, 9.995 meter. Not repeating that. Finally, if we go to the DMAC, that is the mutual distance of A and C phase. Let us explore what are the different options available. First we have A1C1. First we have A1C1. Then we have A1C2. Then we have A2C1. Then we have A2C2. And we have fourth term, so you should take fourth root. So what is A1C1 is equal to A1C1. So the distance from A1 to C1, you see, it is distance from A1 to C1, it is 20. What is A1 to C2? This A1 to C1 is 20 and C1 to C2 is 40. So it will be 20 plus 0.4. So 20.4. A2 to C1 it will be 20 minus 0.4. A2 to C1 it will be 20 minus 4, that is 19.6. And lastly A2 C2 again it is 20. So if you take fourth root, so this will coming out to be as 19.997 meter. So you have evaluated all the three mutual distance. So now we can calculate equivalent mutual distance as, we have three terms, so we have to take cube root. So we have 9.995 twice, so you should take square for these two terms. And last we have 19.997. That is coming out to be 12.59 meter. Now when you calculate the ds for this geometry, the self distance for A, self distance for B and self distance for C will be exactly same. Why? Because you see, if you evaluate A1 to A2, these are the self distance. So there are two combinations. One is A1 to A1, another one is A1 to A2. What is A1 to A1? It is the radius, and A1 to A2 it is the 40 centimeter. So this will be the same for every possible combination. This will be the same for every possible combination. For B1 to B2, so it is B1 which is the radius, and B1 to B2 which is 40 centimeter. And same for C1 C2. So what is that, what is the result? It is the square root of, now what is the distance? 0.7788 into R. What is R? R is actually 1.2 centimeter. So it will be 0.012 meter. 0.012 meter. Okay. And into 40 centimeter into 10 to the power minus 2. So this represents either A1 or B1 or C1 and this represents either A1 or B1 or C1 So if you calculate this, it will coming out to be 0.061. You can always check these values in your home. Once you have evaluated these three values, and since they are identical, so overall equivalent self distance is exactly same, because they are exactly same value. So now we have come at the final stage. Now what is L? So L, as you know, it is 2 into 10 to the power minus 7 ln dm by ds. So we write 2 into 10 to the power minus 7 ln. What is dm? dm is 12.59. Let me check. Yeah, it is 12.59. What is ds? It is actually 0.061. So if you evaluate this, you will get 10.659 Henry per meter. Of course, with the 10 to the power minus 7, that I have forgotten. So 10.659 into 10 to the power minus 7 Henry per meter. So you can write this one as 1.0659 millihenry per kilometer. So if this transmission line runs for a 1 kilometer, it will provide or it will offer an inductance of 1.0659 millihenry for 1 kilometer. So with this, we have solved two different problems of two different configuration, and we have seen that using this GMD GMR method is very easy. You don't need to write or you don't need to require any derivation for this for these two different configuration. Only you need to identify what are the possible distances available. And once you have evaluated that and once you have identified that, you need to only calculate the geometric mean. So by approaching this way, you can solve any problem. You can evaluate inductance and capacitance of the of any tower at any given point of time without having a complete result, ready-made result with you. So with this, I am ending here. From the next class, we shall start the capacitance calculation of the transmission line. Thank you.